On my channel, we are learning the latest, the most advanced AI research and engineering, as well as the next big things. For example, FP4 pre-training is the next big thing that's gonna double the speed of AI training, or almost double, a bit less than double. So we need to figure out how to make neural networks learn in FP4. But for this video, we are going to read this GLM 4.5 technical report. So this is one of the frontier open source, open weight models. And we're just gonna see how they trained it and how they built it and what we can learn from this. And maybe what research questions and research we can get some ideas. I have some courses on coding these LLMs from scratch. So GPT-5, Qwen 3, Llama 4 and DeepSeek. It's like 1 to 3 hour long courses. You can check them in this GitHub repository. And our goal is to make open source reach be equal to closed source research by the end of 2026. So big companies, they can have more compute and get a bit better models because of more compute. It doesn't matter. But we don't want to be behind on research. And this is good for these frontier closed source companies as well. They're going to make a lot of money. They're going to get a lot of frontier research for free. And everybody will be happy with this. So GLM. This is a mixture of experts model with 355 billion parameters and 32 active parameters. So they have a hybrid reasoning model that supports both thinking and direct response models. I think lately people have been separating reasoning and non-reasoning models. So I think this was an experiment that people tried and figured out it's better to train separate models like DeepSeek V3 and DeepSeek R1. But maybe some companies think it's better to combine them, so I'm not sure 100% here. And then AIR model, which is supposed to be smaller, it's very big also, 100 billion parameters. Benchmarks are pretty good, it's an open source, open weight model, it's pretty good. GLM 4.5 outperforms Gemini 2.5 Pro on this SWE-bench verified coding, agentic coding benchmark. And it's close to Sonnet 4. Of course, Sonnet 4 and Opus are best models in coding. They open source their benchmarking code here. So there is one shared expert in the architecture, experts active per token 8, and 160 total experts, a lot of different experts. This is then such compute saving. 96 attention heads, it's a big model. When I code my own LLM, I have like 8 attention heads. Mixture of experts, intermediate dimension, 1500. It's actually not too big. But look at this dense intermediate, 12,000, that's crazy. I have like around 1,000 intermediate dimension on my small language model. So some of the layers have dense feed forward and some of the layers have mixture of experts, which is most of the layers have mixture of experts. And this part is absolutely huge. You know, it's a matrix and this is the number of rows. And we have two matrices. So in one matrix, this is number of rows, the other number of columns, and I guess the other number would be a model dimension. This one, hidden dimension. So I think this matrix is 5,000 times 12,000, absolutely ginormous matrix. And then times 2, because it's going from 5 to 12 and 12 to 5 again. So that's just one dense layer. I can't wait for Gemini 3, it's gonna be so much better at explaining, but I really like Gemini 2.5 for explaining things. And 3 is coming soon, I think, like in a few weeks. The routing, the choosing of experts is using this loss-free balance routing with sigmoid gates. A good routing mechanism would pick the correct experts and it would balance. It would not just choose like a few experts, it would balance to all our experts. Not just few experts every time. Traditionally, there would be auxiliary loss. So besides the loss of predicting the next token, there is also a loss of choosing the next expert correctly. So there would be a loss for the router if it chooses only a few tokens too often, then it will get punished. So it learns to distribute the choice, the tokens for different experts. The problem with this is router might be trying to improve the loss of predicting the next token, but another loss is pushing it to choose different experts. So those two losses could be colliding. Also, there are more hyperparameters to tune, and it makes it just more complex to have two different objectives, two different losses. There is this new way, loss-free balance routing. So this method is also balancing, so tokens are sent to different experts, but without using loss. So this network just learns to look at the token and connect it to choose expert, and there is no additional loss specific for this network. It's just using the overall loss of next token prediction. So for each token in batch, a gating network produces a raw score for every expert. So single token score for every expert. And then all of those scores just get pushed between 0 and 1, because there were some other number before. So that's done using a sigmoid function, but it's important just they get pushed between 0 and 1. You see here sigmoid function, so if score is -6, then sigmoid will get very close to 0. If score is -2, then sigmoid will be here maybe 0.25. And so you see how we can convert any score on X into any sigmoid value between 0 and 1. And of course, the lower you go values on X, it's going to be closer to 0. And higher values on X will be closer to 1 here. It can go indefinitely. Then there is assignment algorithm. This is the part that's replacing the loss part. Takes all of the scores as input, and the scores for single token don't need to add up to 1. It's not probability distribution, it's not softmax, it's sigmoid. It's just all of the scores pushed up between 0 and 1. It also keeps count of capacity for each expert, how many tokens can be pushed to those experts for this to stay balanced. So it's just gonna assign token to the highest, most suitable experts with highest score, but if one expert starts getting too many tokens, it's gonna then choose other experts that are also as highly suitable with highest score as possible. So this is just an algorithm, there is nothing to learn here, it's just a clever trick to remove like loss and learning and make it simpler and easier to train. So they use this math formula to first calculate capacity for each expert. Total tokens in batch times experts to pick per token, which is 8, divided by total number of experts. So for example, there is 1000 tokens and 8 experts, so every expert can take 50 tokens for this batch of tokens. And the way it works, this assigning is done in the planning phase. So all of the experts get 50 tokens, but there is no computation yet. Then when the planning finishes, then everybody starts working all at once. So every expert is processing their 50 tokens, for example, in parallel. That's how it's then training. Because in training you have full data, so you don't need to wait for the next token to be generated. In training you already have all of the tokens, so you can just train in parallel to predict the next token for all of the tokens. It's using grouped query attention. First of all, this is old for years and years. I don't know why this hasn't evolved. Secondly, why are companies not using DeepSeek's multi-head latent attention? I think Kimi is using, or maybe Minimax, I'm not sure. But I'm not sure why other companies are not using it. Maybe it's a bit difficult to figure out. They're also using partial rope for positional embeddings. The thing is, this architecture hasn't evolved for 3 years. We need to figure out better architectures, people. What is this? They actually use a lot of attention heads, 96, which is 2.5 times more attention heads than comparable models. They say while this didn't improve training loss, it actually improves performance on reasoning benchmarks like MMLU. Classic query key norm. We need to step up inventions of new architecture, guys. What is this? This is old. All of this is old, like 2-3 years. They also have a dedicated multi-token prediction layer. It's a speed up for inference to help the model predict multiple tokens at once. Then pre-training data, it includes documents from web pages, social media, books, papers, and code repositories. They carefully process data, as one should. The majority of our pre-training documents are English and Chinese web pages crawled from the internet. And then, like in Nemotron CC, they divide the crawled web pages into buckets of different quality scores. So they discard low quality and keep high quality. This way, this helps model learn the long tail world knowledge, the details, edge cases. This long tail knowledge is the main issue with synthetic data because it's uniform and there is no many different diverse edge cases like in the real world data. So that's why models are struggling to train on synthetic data. But this is about to change, I think, in the next half a year or 2 years. OpenAI also said that they figured out a lot better how to train on synthetic data. And I think this is one of the things where you don't need more compute. So here, open source research should be ahead of closed source companies because there is more of us. And we should work hard to have best frontier science open. They also found that there is a lot of similar web pages that are generated with templates and they all got high scores. So they went undetected in their min hash deduplication and scoring. So they applied this other technique, SEM dedup, to remove those highly similar web pages based on document embeddings. This is interesting. In pre-training, they have a general pre-training corpus 15 trillion tokens, 4K context window. And then they have 7 trillion tokens on code and reasoning continual pre-training corpus. And then repository level code data, 500 billion tokens and 32K context window. Synthetic reasoning data, that's a lot of synthetic reasoning data, but it's not too much where the model starts to collapse or something, where it changes weights too much. They maybe even have learning rate scheduler, so these are not gonna influence or change weights as much as these in the beginning. But that's just a guess that everybody is using, so I think they're also using it. And then long context, when they extend the context window where they need to train on this long context data, 100 billion tokens, and agent data. This is pretty cool pipeline. I like it. I'm still trying to understand the data. I think I know architecture way better than data. So that's one of the next things I'm trying to figure out. They're also using this Fine Web 2, which is openly available dataset that you can use to train models. It has trillions of tokens, I'm pretty sure. And they are using their own data. So these open source repositories or data sets are very popular, and then companies have their own data as well on top of that. When they are creating coding data set, they classify code into high quality, medium quality, and low quality. And then they disregard low quality data and upsample high quality code, not sure what that means. And then they also have this fill in the middle training objective. This describes their coding data processing pipeline. I think it's interesting. Then they have math and science. So you can also train a small language model to predict the score the classifier scoring function would give, which they do here. They also have this mid training that I was explaining. It's about code, math, science, agentic data, agentic and long context. So repository level code training is they concatenate files from the same repository for the code to learn cross-file dependency. This is what Anthropic is doing, I'm pretty sure. Claude is such a good model, I cannot stop saying that. It enables so much coding, so much software will be soon built on Claude and other models maybe. They're using MuP Optimizer. Yes, everybody's gonna start using MuP Optimizer. It's gonna, I think, almost 2 times more learning from same number of tokens. And this is for 2D matrices, so it's applied to all parameters except word embedding, bias, and weights for RMS norm. So Gemini just explained what upsampling documents mean. It means showing that document more frequently because it's high quality. Then for Newton-Schultz in MuP Optimizer, number of iterations to 5. I actually was trying I was trying different iterations. I got on my small neural network that 10 works better, but maybe they tried it 5 works better. I'm not sure. We observed that MuP Optimizer can accelerate convergence, yes, and tolerate larger batch sizes or more different learning rates as well compared to AdamW. And by the way, they're going to use AdamW for these other parameters that are not using MuP. They used a cosine decay schedule for learning rate instead of warm-up stable decay schedule, because they found in early experiments that warm-up stable decay performs better on these, or worse on these benchmarks. They're using quite a low, surprisingly low learning rate. Maybe not too low, but I would expect MuP to use 0.01, but they're using a lot smaller. But I mean, they probably did experiments and this is what works best. They also used batch size warm-up strategy, where they gradually increased batch size from 16 million tokens to 64 million tokens. These are huge batch sizes, because I train on one GPU, so my batch size is a lot smaller. And they did this warm-up for the first 500 billion tokens, half a trillion tokens. And then it remained consistent for the rest of the training. I guess it's 64 million tokens. They don't use dropout, which I noticed that LLMs don't use dropout for some reason. But when Claude is coding, my LLM, it gives me dropout. And weight decay ratio 0.1 I think is pretty standard. So weight decay of 0.1 means reduce weights by 10% of their current value, scaled by learning rate each iteration. So this is it. We have the weight times weight decay times learning rate. So we subtract that. So that's just a bit of reducing weights by a little bit, so they don't explode and become big. I guess we want smaller weights on neural networks generally. So usually the learning rate is also very small. So when you multiply very small learning rate and very small weight decay, you're gonna get a very, very small reduction. 0.0005 in this case. And over many steps, this 10% times learning rate small reduction compounds. So in the beginning it's 0.001, but after 1,000 steps you have a lot bigger reduction. This is because weights tend to grow bigger, so we have compounding reduction of the weights because they tend to compound to become bigger. They're using gRPO, which is interesting. It's getting more reward during the training as it's learning more. In their reinforcement learning, they are combining multiple methods like rule-based feedback, human feedback, and model-based feedback. They have instruction following reinforcement learning, function calling reinforcement learning.
I think that's gonna be it. I don't see anything interesting. These evaluations, some prompts, and that's it. Okay, so thank you for watching and see you in the next video. Bye bye.